Today's lesson is going to be about chemical change graphs. So, some things to think about. The first two graphs we've learned about are about the heating curve and the physical or phase change diagram. Both of these types of graphs deal with physical changes that happen to a state of matter when it goes from a solid to a liquid to a gas, and what happens at critical point and at the triple point. Today, we're going to talk about what happens when an actual reaction takes place where chemicals change and rearrange to become something else. So I'm going to look at two different equations here to start with. So the first one I want to talk about is CO2 plus H2O, and it is going to produce C6H12O6 plus O2. This is common in what happens inside plants and is known as photosynthesis. And if we're photosynthesis to happen, we have to have the sun to provide some energy and heat to get these compounds to rearrange themselves to produce glucose and oxygen. Because of this, it is storing energy. It's creating energy that we as animals can eat, and this type of reaction is known as endothermic. If we reverse this equation and we do C6H12O6 plus O2, and it breaks down into carbon dioxide and water, then this type of reaction is known as cellular respiration. And this reaction, since it's going in the opposite direction, when we consume plants and we breathe oxygen, we produce and generate a lot of heat, which is why we're warm-blooded animals. And what this does is this reaction then becomes exothermic. So any reaction that goes endothermic in one direction, when it goes the opposite direction, is known as exothermic. What we're going to look is at some heating curves of what does this look like for the different types of reactions with energy. So the first one we're going to look at is endothermic. We're going to have an X and a Y on our quadrant 1 graph. And down below, we're going to have time, and this can be in seconds. And over here, we can have energy in the form of heat, and this will be measured in joules. I'm going to put some numbers on this graph, and let's say that we have 100 joules. Let's say that we have 300 joules. And let's say that we have 350 joules. We're going to start out by bringing it down this way, and then we're going to go up to 350, and we're going to come down to 300. So we're just going to connect it with an exponential curve, going up and then going down. On this part of the graph, we're going to call this Q initial. So that is our initial energy. And over here, we're going to have QF, which is going to be Q final. So our final energy. And then we're going to have, if I had a dotted line right here that went across, and we're going to have an area here from the peak of the curve down to the bottom. And we are going to call this pink area, I'll just call this number 1. So our number 1 area, this is called the activation energy. We can also look at this and find what's known as delta Q, which is the change in energy. And if we remember, endothermic is where Q is going to equal a positive number. And if you look by putting a pencil on a piece of paper, looking at these 2 points here, you'll notice that my pencil goes in a positive direction, meaning that this has a positive overall slope for its average, which is what makes this an endothermic reaction. And if I actually calculate it out, my Q final minus my Q initial, and my Q final was 300 joules, and my Q initial was 100 joules. So my delta Q in this case equals 200 joules in the positive direction. So that makes this reaction endothermic. So what is activation energy? Let's talk about activation energy here. So any reaction that takes place is going to need some kind of startup energy. So activation is that. It is the energy required to make the reaction start. And then if we think about this over here, under QI, this is where our reactants are. And over here is where we have our products. And then everything between QI and QF is where the reaction is taking place. So it's undergoing change. All right, so that is for endothermic. Now let's look at what happens in an exothermic. Because of the law of conservation of energy, energy is always transferred, and it's transferred equally. It cannot be created nor destroyed. So in this case, we're going to have a mirror image of our endothermic reaction for it to be exactly the same going in the opposite direction. So again, if I start with my X and my Y axis, we're going to have energy in the form of heat, and our measurement here will be joules. And then we're going to have time, and this can be in seconds, it can be in any time frame. And let's say that this is 100 joules, and we have our 300 again, and we have our 350. So this time our Q final will become our Q initial. So if this was at 300, this will be at 300 for its initials. This is our Q initial. And we have the peak up here, which is 350. And then down below, we have our 100, which is where we end up. And this will be our Q final. So we go up again, and then we come back down. This time, if we're looking at the activation energy, our activation energy is significantly different. And so before we started all the way down here, because that's where we started with Q initial. We're not going to start down at Q final, but Q initial, because where are we starting with the energy and how far up do we need to go? So our activation energy up here is much lower to get it started. So again, if we notice that our slope here, if we look at our pen, our slope is going in a negative direction, meaning that our Q will be negative. So our change in energy will be still Q final minus Q initial. And our final energy was 100 joules, and our initial energy was 300 joules. So we get negative 200 joules. Again, it has to be negative for it to be exothermic, releasing that energy. And again, we still have an activation energy, but the activation energy is lower here. One other thing I want to talk about with you guys is what's known as a catalyst. So a catalyst lowers the activation energy. So when we look at this activation energy for here, we see a higher peak, and our catalyst is going to actually make it a little bit lower. So instead of it taking 50 joules of energy, in this case, maybe it only takes about 10 joules of energy. What a catalyst does not do is it does not make a reaction that could not happen. So it can only make reactions that already would happen. It just lowers that activation energy. You might have also heard that it speeds up the reaction. If you notice here, it's not that it necessarily speeds up the reaction, it just requires a lot less energy to get it started. So in essence, because it can start sooner, but it still ends at the same amount of time. Let's look at this example to determine how to draw a graph based on information. So how much total energy absorbed or released if an initial energy is 100 joules with an activation energy of 300 joules and a final energy of 350. So the first thing that we need to do is we need to look at the numbers that were given. So we have QI, QF, and then our activation energy. So we're going to draw our graph, and we're going to start with 100 joules. Now you might think that we're going to go up to 300 joules here for our activation energy, but what's happening is, remember, that is your initial starting point. You need to go up 300 joules. So really what's happening is we need to get to 400 joules. So we're going to start at 100 and we're going to go up 400 to 400 because this activation energy here is going to be equal to 300 joules. Then we're going to end at 350 joules. So that number doesn't change. So we're going to end here at 350 joules. This is our Q final and this is our Q initial. So when we look at our change in Q, we are going to have our 350 joules minus our 100 joules. And what we're left with is 250 joules. And again, we can look at the slope, or we can even look at the value of Q and realize that we have a positive overall slope. So this is an endothermic reaction.